Hello everyone. This session is basically a continuation of part 1 of section 1-3, which is based on finding limits analytically. So in part 2, to find the limits analytically, we are going to look at some special functions of rational and trigonometric functions. So we'll start with a rational function, and this is the one I have done a lot in this videos. Now, the one I'm going to look at is the limit as x approaches 1 over x cubed minus 1 divided by x minus 1. So this, remember guys, is the function. Okay, this is my function. Notice when I plug in x equals 1 in the denominator, the function is undefined. So the idea is there anything else? Can I get something more information, some more information about this function? And yes, calculus gives us a lot of information about it. So that's what you're going to do, is study the behavior of this graph of this function near x equals 1, which led us to the whole limit concept. We learned using graphical and numerical approaches that the answer to this expression or this function is a 3. Here we're going to apply the analytical ways, and in the specific function here we're going to divide out a common factor. Okay, so let's do that first. I've already drawn this function, the graph of this function on the left-hand side of the slide. Notice that this function at x equals 1 has a hole, and the value of the limit is 3. Now to do it analytically, what we're going to do is we are going to look at the expression. And as I said, we're going to divide out a common factor. Now, I cannot do anything in the denominator, but numerator has a lot of potential. If you guys remember this formula, a cubed minus b cubed. It is a minus b times a squared plus ab plus 1. Now, in our expression here, my a is x and my b is 1. So the numerator becomes x minus 1 times x squared plus x plus 1. So this whole function now has an x minus 1 in the numerator and denominator, and we can easily cancel it out. We are left with limit x approaches 1 of a squaring function given by x squared plus x plus 1. And we already see the graph here, and there's no issue in the denominators. We just go ahead and do direct substitution. We get the answer as 3, which we already had seen earlier. Now I'm going to talk about a very special case here, is what kind of this function is basically talking about. So let's go to that special concept here, is the indeterminate form. And we will be visiting indeterminate forms later also in this course. So this is our first introduction. What it simply means is that when we apply direct substitution to this example, limit x approaches 1 over the function x cubed minus 1, x minus 1. So if I put basically directly substitute here, what am I going to get? I'm going to get a 0 by 0 function. So when you substitute x over 1, we're getting a 0 by 0 form, which gives us no answer. A limit of a 0 by 0? No. But we know that the limit is 3. So this indeterminate form does not guarantee, first of all, that a limit will exist. So any expression, that any expression which gives a 0 by 0 form is called an indeterminate form. So let's talk about the definition. Now, some serious thoughts over here too. Indeterminate form does not guarantee a limit will exist. And suppose a limit exists, it does not tell us what the limit is just by looking at it. We have to use some techniques to get the answer. One of the techniques we just did was dividing out a common factor. So let's take another example of that. So over here, we would like to find the limit as x approaches 2 of the function x squared minus 5x plus 6 divided by x minus 2. Now notice when I plug in 2 directly into this function, what am I getting? A 0 by 0 form. Notice, as I said, this is an indeterminate form. Now the limit may or may not exist, but we will try a technique here called dividing out a common factor. That's the only thing we have learned, by the way. Notice the numerator is a squaring function, and we can easily make factors of x squared minus 5x plus 6, which is given as x minus 2 times x minus 3 divided by x minus 2. So we want to take the limit or as x approaches 2. So that's a little typo, guys. This is x approaches 2. Okay, so coming back to the problem. Notice the numerator and the denominator both have x minus 2, a common factor, which we can remove. And that was also x minus 2 was a problem for us, remember, because x is approaching 2. So what are we left with is limit x approaches 2 of x minus 3. And when we do direct substitution, we get the answer to be minus 1. Okay, that was one technique. Let's look at another technique. It's going to be the next slide. Here, the limit as x approaches 3 of the function square root of x plus 1 minus 2 over x minus 3. Once again, when I plug in a 3 here in the function, I get square root of 4 minus 2, which is basically a 0. And then when I plug in 3 in the denominator, I get again 0. So again, this is a 0 by 0 form. And we also said that if we apply some techniques, we can get answer. Now in this problem, guys, we have a square root. And there's no easy way to make factors of it. But if we apply a different approach, because these are rational roots, and if we rationalize the numerator or denominator, we might be able to get rid of the square root. And that's the technique we're going to use here. And the idea is this difference of squares, a squared minus b squared. Which is a minus b times a plus b. Now when you take the squares, clearly the square root will vanish off. So what you're going to do is we're going to rationalize the numerator by multiplying by square root of x plus 1 plus 2 divided by square root of x plus 1 plus 2. Very important, guys, we cannot change the original problem. But if we multiply by the same number and divide by the same number, we are basically having the original problem itself. Now let's go ahead and do multiplication of the two numerator terms here. So what we find is this is square root of x plus 1 is your a and 2 is your b. So when you multiply square root x plus 1 with x plus 1, you get rid of the square root, we get x plus 1 minus, and 2 times 2 is 4. The denominator we have is x minus 3 times square root of x plus 1 plus 2. Now it's simple algebra here. So solving the numerator, we get an x minus 3 in the numerator, and we already have an x minus 3 in the denominator. We can nicely cancel this out. And now we're left with an expression 1 over square root x plus 1 plus 2, and we can easily find the limit for this one. Because there's no problem in the denominator, so when we plug in the 3 by direct substitution, we get 1 over square root 3 plus 1 plus 2, which is 1 over square root 4 plus 2, which is 1 over 2 plus 2, 1 over 4. Okay, so we have learned how to solve rational functions using two techniques. One is dividing out the common factor, and second is by rationalizing the expression. Either you can rationalize the numerator or the denominator depending upon the problem. And as usual, I always give you some practice problems. They are related to the things we have done earlier. These are the very similar kind of examples I've done, so I want you to practice them. Now, the last thing we're going to do in this part 2 of section 1-3, we're going to look at special trigonometric limits. So the first one, limit as x approaches 0 of sine x over x is 1, and the limit as x approaches 0 of 1 minus cosine x over x is 0. So let's look at some problems. Limit as x approaches 0 of sine x over 7x. Now notice that in the the expression sine x over x, the argument next to the sign is exactly being duplicated in the denominator. And that's where when x approaches 0, you get the answer to be 1. Here, we do not have that. But if we do some manipulation to this function, we actually might get this expression. So let's do that. So the limit x approaches 0, I can write this function as 1 by 7 times sine x over x. Now 1 by 7 is a constant. By applying the basic limits, we can take the limit outside, or the properties of limit here. Limit x approaches 0 of sine x over x. Now remember, this is a 1. So the final answer, 1 over 7 times 1, 1 over 7. Simple. Okay, now let's look at the next problem. It says, limit x approaches 0 of sine of 5x over x. Now remember what I said. The formula is sine x over x. The x and the x match. Now here, next to sine is 5x, but we do not have 5x in the denominator. But we can make it. Remember, I can multiply and divide a constant. It won't affect my original function. So I can do is write limit x approaches 0. I can write this as sine 5x x. Now I can multiply by 5 in the denominator and multiply a 5 in the numerator. Now, there is no problem because my original function is still there. Now, let's look at this expression, sine 5x over 5x. So, if x is sine x over x as x approaches 0 is 1, so sine of 5x over 5x is kind of the same. It's basically going to reach faster to 1. So what we're going to do is, the only idea remember is, I'm not going to go deeper into why and all those things. Just remember that when you're solving these problems, I'm just giving you some little hints to do it. When you're having a sine x over an x, the expression next to sine should exactly be mimicked in the denominator. So if you have a 5x, I should have a 5x in the denominator. And then you're multiplying this whole expression by 5 by simply the, scalar multiples of the limits. We can take the 5 out. So limit x approaches 0 of 5x sine 5x over 5x. Now this we know the limit is 1. So the answer is 5 times 1 is a 5. Okay, let's look at another example. Limit as x approaches 0, 3 times 1 minus cosine x over x. Now remember, it's a constant multiplied the expression. So I can take the constant out and write limit as x approaches 0, 1 minus cosine x over x. Now remember, in the previous slide, we said the limit of 1 minus cosine x over x is 0. So here, it is basically 3 times 0, which is basically a 0. So the final answer is a 0. Okay, let's look at the next problem. It's a cosine with a tangent and an x. Now we only know those two special trigonometric limits. And here we have nothing which is similar to what we know. But if you look in this problem, and if you remember your trigonometry, a tangent has some relation to sines and cosines. So what we're going to do is, before we apply the x over approaches 0 to this, let's see if we can cancel certain things out. Okay, so let's write that down. So limit x approaches 0. Cosine x, nothing can be written, but we know tangent x is what? Sine x over cosine x, the whole divided by x. Now clearly, cosine x and cosine x here, they can cancel out. What are we left with? Limit x approaches 0 of sine x over x. Now this limit we already know. The answer is 1. Okay, let's look at a little bit more harder problems. Now here, we would like to find the limit as x approaches 0 of tangent x over x. Remember, we have no idea for the limits for tangent. And if we go back to the previous slide and apply the things we know, we can get answers here. Okay, so let's go ahead and now basically focus on this function tangent x over x with the things we are more comfortable with. Now remember tangent, so I can write this as 1 over x times tangent x, right? I'm just going to do simple algebra, guys, and some trigonometric. So 1 over x tangent x is what? Sine x over cosine x. Now remember, do not forget your limits, guys. Now I can just rearrange this expression and say limit x approaches 0 sine x over x times 1 over cosine x. Now notice this is a product of two functions, so we can do this as limit x approaches 0 of sine x over x times limit x approaches 0 of 1 over cosine x. Now sine x over x is x approaches 0, guys, is what? A simple 1 times, now 1 over cosine 0. Now remember, 1 over cosine 0 is what? Cosine 0 is 1. So it is 1 times 1 over 1. So the final answer is a 1. Okay, let's look at what we are given in the next problem. The next problem says, limit as x approaches 0 of sine 2x over 3x. There is no x's in the denominator, but if we play with it, with this function sine 2x over sine 3x, we will get an answer. So let's play with the sine 2x over 3x here. Limit x approaches 0. I can write this as sine 2x times 1 over sine 3x, right? Okay, now let's look at 2x. It is missing a 2x in the denominator, remember? We need a sine x over x or 2x over x. So what we can do is, we will multiply this by 2x and divide by 2x. So I can multiply and divide by 2x. Okay, let me write it much more nicer here. Okay, now sine 2x is kind of taken care of. Let's look at sine of 3x. Now I can multiply and divide by 3x because we want a 3x in the denominator, and I can also multiply this whole expression by 3x. Now notice I can rearrange a little bit of that and see what we can get. Limit x approaches 0. We have sine, so we have sine 2x over 2x times 2x, now that was the one we added, times 1 over sine 3x over 3x, and I can write this as times 1 over 3x. Notice? Everything is a multiplication, guys, here. Okay, notice this x and this x can be easily cancelled. And what are we left with? A 2 and a 3. These are constants, so you can simply plug that out. We can take the 2 out and divide by 3, and what are we left with? Limit x approaches 0, sine 2x over 2x times 1 over sine 3x over 3x. Now remember, this is a product of two functions. So this is equal to 2/3. A product of two functions is the limit of them separately. So which is limit sine 2x over 2x as x approaches 0 times, now we can take the limit in the denominator, and the limit in the numerator of a 1 is always going to be 1. So this is going to be limit 1 x approaches 0 over the limit x approaches 0 of sine 3x over 3x. What do we get? 2/3. A limit as x approaches 0 of sine 2x over 2x is what? A 1. Times limit of 1 as x approaches 0 again is a 1. And in the denominator, limit x approaches 0 of sine 3x over 3x is a 1. So clearly the final answer is 2/3. Okay guys, we have done our examples on trigonometric limits. Now it is going to be your turn to practice. So here are the practice problems, very similar to the examples I have done. Thank you.